Let's now look, we talked about ionic bonding. Now let's talk covalent bonding. This is a little bit weaker than the ionic bond, but it's still quite prevalent and it's quite fairly strong. And we interact with many materials that are covalently bonded. Here, because the interaction is a little bit weaker, the non-metal is not strong enough to take away or steal or whatever the electrons of the other partner in this. Okay, and what we say is that instead of being stripped of its other electrons, they're all sharing equally. Well, to some degree, they're sharing their electrons. Okay, and let's look at an example of chlorine. Chlorine is a molecular. It's a molecular compound, and each chlorine has 7. Let's see here, 7. If each one of them says, we can just share this electron and pretend like we both have, shared custody of this, and this one says, yeah, I'll share this one's custody, like that, then I can sort of ignore this, like, and look at this guy, and he's like, I have 8, and then this guy can ignore the other one, says, look, I have 8. So they both have 8. So in the mind of each one, they each have 8. And then the way we in chemistry denote this is when a pair of electrons is being shared between two species, we denote that with a bond. Okay, so there's a bond right here. We don't write the 2 dots, and we make this into a bond. We also don't write this in reality, right? This is just to help us right now. So you would see chemists often write Cl-Cl, and this means that there's a single bond between the 2 chlorines, okay, when they're sharing one pair of electrons, right? Let's look at how we draw the loose dot diagram of the loose structures for other binary compounds. Okay, so the way we do this, the recipe for this, is that we draw the loose dot diagram for each of the atoms separately, and then we determine how many should be shared so that the octet rule is satisfied. Okay, whenever whatever is being shared, and for every 2 dots, you replace with a bond, right? I will note here in red, very important, hydrogen and helium do not follow the octet rule because they don't need 8, they need 2. Helium has 2 around it and it's pretty happy, and hydrogen also. And look back at the quantum stuff we did to look at the s orbital to see why hydrogen and helium only want 2. The rest of the elements would want more. Well, I mean, lithium and beryllium by extension are going down to 2, but don't even worry about that. But helium and hydrogen only want 2. So hydrogen here says, I really need 1 more. Chlorine says, I also only really need 1 more. So they say, let's just share what we have. And H, as far as it is concerned, and there's a blue circle, says, look, I have 2, I'm happy. And Cl says, look, I have 8, I'm happy. And then HCl forms one single bond between them, HCl, this way. Okay, and then you can or not omit these dots. All right. Let's look at another example, nitrogen gas, okay, which we've seen before. Nitrogen gas is the, N2 is the natural form for nitrogen. So they each have 5, and they want 8. So they say, if we only share just the 1, well, if I put them and smush them together, this will have 1, 2, 3, 4, and then if they share 1, 5, 6. That's not the octet rule. That's not happy. So they say, let's share 2. So let's actually look at it on the whiteboard. Oops. Let's say I have n, 1, 2, 3, 4, 5, and another n, 1, 2, 3, 4, 5, and they say, let's share 1. So if they share 1 and they get together, okay, if I look at this circle here, this one has 1, 2, 3, 4, 5, 6. That's not the octet rule. If I look at this circle here, do a square. This one has 1, 2, 3, 4, 5, 6. It is not happy. It's not the octet rule. So they say, okay, let's try to share 2. Like this. If I look at this circle right here, this one has 1, 2, 3, 4, 5, 6, 7. Not happy. This one has also 7, not happy. So I say, let's try 1 more. Let's try to share 3. So they each bring 3 to the table. And so if you look at this circle here, 1, 2, 3, 4, 5, 6, 7, 8. If you look at this circle here, also 8. So they're both happy. The octet rule is satisfied. And as a rule, we said for every 2 pairs, I replace it with a dot, with a dash. So I have 3 pairs. It will look like this. And I can or not omit these 2 things. I can just write it like this. What we call this is a triple bond. Okay, this is a triple bond. We could look at another example of oxygen. Oxygen has 6. Here too. 1, 2, 3, 4, 5, 6. If they share just 1, okay, oxygen is by natural form, it looks like this, right? If they share just 1, like this, I think. I confused myself. I'm sorry. Got distracted. I'm allowed. 1, 2, 3, 4, 5, 6, 1, like this. Okay, so if I look at this circle, I have 1, 2, 3, 4, 5, 6, 7, and this circle, I also have 7, not happy. So we'll try it again. And this time, I will share 2, like this. If I look at this circle, I have 8. If I look at this circle, I have 8. I'm sorry, I lost these. I have 8. And now this will have a double bond. So that's how you get a double bond between the 2 oxygens. Great. Okay, so this is a triple bond. We have a double bond. So multiple bonds are things you see in chemistry quite often. You don't see much more than triple bond. You see a single bond, a double bond, and a triple bond. You don't see a quadruple bond. That doesn't happen really. And so they share more electrons and they're stronger than a single bond. And so N2 is very non-reactive. As you remember, as you know, nitrogen is known to be extremely inert and it does not react. And hydrogen is much more reactive than nitrogen. Okay, oxygen is going to be more reactive than nitrogen. And it is, we indeed see that things get oxidized by oxygen. Okay, you can also see that it's the length between the distance between 2 atoms that have single bonds, double bonds, and triple bonds. If they have a single bond, they're very far apart. Not really far apart, but quite far apart. This is in angstroms, by the way. I didn't write the units. It's an angstrom, times 10 to the minus 10th meters. Here they're closer, and here they're closer still. Okay, let's look at how we do Lewis dot diagrams, Lewis structures for multiple compounds. We have just more than just a binary.